And then kind of what I figured we would do is cruise through it. We'll talk about neuroscience of the future of space travel. Not of space travel, because there's a whole different kind of neuroscience of what happens to the body when it's actually in orbit without gravity. It's really cool stuff, but we won't have time for that today. Today I want to share a little bit about what the mission was that I did, which was preparing to go to a long-duration trip like Mars, and more on the psychological and cognitive neuroscience side of what might have to be accounted for in terms of managing isolation and confinement and working together effectively in teams. Sound pretty good? So I've been asked to do sort of 4 things all at once, and I'll try to explain that to you guys, what I mean by that. And so, what I'm going to try to do today is aim to accomplish this sort of, and you can kill the lights to the extent necessary back there, whatever's a good blend of what you guys feel is a good fit. But I was asked to basically talk about 4 different things. 1, I was asked to talk about my scientific research into the cognitive neuroscience of memory, and 2, I was asked to talk about the NASA mission, which are sort of different. There's a lot of relationships and overlap, but they're actually 2 different kind of talks. So I just sandwiched both of those together at once. And then I was also asked to do 2 things on top of that. 1, I was asked to give it to a room full of some of the world's top neuroscientists at UC Davis, really sort of advanced doctors and scientists who really want to get into the granular nitty-gritty of all the stats and graphs and crazy scientific details. And then I was also asked to give it to a room full of the same people filled with donors and other people who are open to the public, who are just interested in space and don't know anything about neuroscience. So those are 2 really different things about 2 really different topics, and I'm going to try to do my best to slip back and forth between the 2 of them, see if I can satisfy all the kind of demands for the people interested in just cool, sort of superficial, entry-level stuff into understanding a little bit about psychology and neuroscience and space, and then of course try to satisfy the people who might be interested in a little bit more depth. Does that sound like a good deal?
Yeah.
Okay, I'm going to try. We're not sure we're going to hit all those notes, but feel free to send me an email with feedback when we're done. It'll actually really help me. We can't learn if we don't get feedback, and I am just a glutton for always trying to improve and get feedback, so it's really useful. And do you guys want to change the lights at all so it's darker up here? Yeah, can you see if you can play around with them? Wait, is that better? Okay, cool. So, anyways, today I'm going to be basically talking about brain states and the journey, kind of how we can go from research on memory into this mission that was a simulation for what it might be like on a trip to Mars. And so I'll explain kind of how that connects here, because the kind of core question becomes, why neuroscience and why Mars, right? And so I'll share with you a little bit about some basic answers to that simple fundamental question, right? How does the brain connect to Mars? Well, for one thing, we need our brains to get to Mars, but we also want going to Mars to protect our brains from things like radiation exposure and things like that. But more importantly, there's a real core part of psychology that's going to play a really important part, that if we screw it up, I would like to persuade you that we will not land on Mars without the right psychology. And here's what I mean. We've got to go from spot number 1 here. You are here on Earth. We want to get to spot number 2 here, which is on Mars. Difficult enough as it is, but our machines are already landing there. The robots are doing it. We're there. Here's the thing. We also want to do this thing called coming home. Yeah. Right? And here's the toughest part of all. It's not landing on Mars. It's not coming back. You must survive each other for 3 years in a tiny capsule the size of a camper that you can't get outside of to breathe fresh air for 3 years. So imagine your 3 closest friends or most favorite family members that you still want to have Thanksgiving dinner with, and imagine taking the longest summer road trip you can imagine, and every time you stop for gas not being able to go out and get fresh air.
Well, tough, huh?
Now imagine it's not your closest family members who you love, or your closest friends who you really like. Now imagine their coworkers. You got to work together the whole time. That's what we got to figure out. Because if something goes wrong, everything can go wrong. Drastic fashion. And so when we go to Mars, our rockets already work, and they will. but will the people work together? And that's the core question. And understanding how people work together is a core component of psychology. Now, as soon as you start talking about psychology, what you really mean is neuroscience, because the mind is kind of based upon the brain. So this is where it all kind of ties together. So if you guys remember the movie Interstellar, we had the brilliant Dr. Mann here, and of course, our hero, Cooper, right? Now, spoiler alert for those who haven't seen Interstellar, this is a fight, and it's about to go down, big time. And like a royal rumble on Mars, and it ruins the entire mission. There's explosions, people die, and they don't come home because there was an interpersonal problem. There was a failure of psychology within a single person, and a failure of psychology of teamwork between two people, and it ruins everything. And so, errors of cognition, that is how we think, errors of teamwork can be catastrophic. And on a mission like this, failure is not an option. Can we at least agree on that part? Yeah. All right, awesome. So that's kind of where our mission comes in. So we did a mission called HERA. Now what HERA stands for is the Human Exploration Research Analog. And what that is an Earth-based facility that is basically NASA's biggest laboratory for experimentally studying the psychology of humans simulating long-duration spaceflight. In fact, it's one of the only facilities like this in the world. Okay, now this is kind of a half view of it. You can see this building here. We have an entry door here. There's a hygiene pod over here, basically. That's where you go to the bathroom. And up here is the second story, and a little third story up here is where our bunks are. Now it lives in this big hangar, and I'll get into showing you guys the actual HAB, which is short for the habitat. And you guys saw the Martian. We'll get into that in a little bit. I'll give you a little bit of a tour a little bit later on in the talk. But that's what we're talking about here, the Human Research Program, and that's what we were fortunate enough to participate in. We were basically this specialized laboratory for testing the states of the human systems that we need to understand, and we don't yet. But we're trying, and that's what this is there for. We need to understand in order to get it right, to get to Mars, to get home, and to get along with each other along the way. Because even if you get to Mars, do you really want to go if you're going to be that miserable for 3 years? 3 years? No, I did. I'll tell you, this is a tough thing to do. Stay in confinement with someone for that long. So, we are the test pilots for the human mind, for these human systems that are needed for deep space exploration. And this is our ship. It's earthbound. It's at Johnson Space Center in Houston, Texas. And we study everything. We study teamwork. We study more teamwork and more teamwork. We're looking at group dynamics. We're looking at team cohesion. All these things that are essential elements. Okay? Remember we talked about group projects last class, right? Yeah, now you see why. Okay. We study nutrition and exercise. They're making us do sleep deprivation and rest studies. We're studying, of course, the psychology and neuroscience, which is what I'll focus on here today. There's also experiments happening in there on us on medicine, microbiology, and botany, studying plants. We've got to grow our vegetables, grow our salads. They're delicious. Engineering and maintenance, we do that in there. We fly flight simulators and lunar landers and operate robotic arms and take virtual reality spacewalks. In short, it's freaking awesome. It's really exhausting, it's really tiring, it's a big challenge, but it is awesome. It's like a dream summer camp for adults who want to go to space camp or are just big dorks otherwise and really love science and exploration. This is fun. So I'm going to share that with you a little bit. Too fast? All right. So, a lot more to come. So, just an introduction to who we are on our mission. So you'll see us going throughout the talk a little bit. Dr. Shelly Cazares is a brilliant engineer. She comes actually here from Southern California in these kind of areas, kind of outside actually a little bit by Bakersfield and Tehachapi. And she has had an illustrious career where she went from Tehachapi to MIT engineering degrees, then to a PhD at Oxford University in England, and now is an engineer at the Pentagon. So she's pretty world-class, fantastic. Reinhold Povolitis is our flight engineer. He operates the Lunar Reconnaissance Orbiter as an engineer at Arizona State. So what that is a satellite that orbits the moon and takes a bunch of digital pictures, and he reconstructs them and does all the mathematical analysis to create actual images of the moon's surface at high def. And he's actually seen pictures of Neil Armstrong's footprints and of the lunar rovers, which is really, really cool. He sent me an autographed picture of the moon for Christmas, which is like really awesome. This guy is like my hero. And so he really is. Awesome dude. Played baseball, did crew and rode in college, and just all around awesome guy. Loves riding dirt bikes in the desert, and just great guy. So our commander was Paul Hagen. He is a PhD in biomedical engineering from Rice University, and has also been a test flight engineer of these fighter jets that the astronauts train in at NASA in Johnson. And he also works with the human exploration program as well on the engineering side. He is an all-around, just amazing guy. Couldn't ask for a better commander, couldn't have asked for a better team. They really were the best. And really, when I mean team here, this is our crew. But we talk about the team in the bigger context. So we have our crew, but our real team, this whole mission, this operation, this is really guided and owned, right? We're just sort of the lab rats ourselves, but this is a mission that's run by an amazing crew of people who are there 24/7, 365 days a year, running mission after mission after mission. They are basically what we call mission control, a bunch of scientists, incredible staff, administrators. These are the people who do an incredible job of running a very, very difficult study. And as a principal investigator myself, running studies here at Cal State, the laboratory, it is tough to run any study. If any of you guys have participated in SONA and stuff, it can be tough to design a good study. And to do these is incredibly challenging. They do a wonderful job. And we were, as I'll like to frame for the rest of the entire talk, we were a tiny, tiny part, our crew, of a huge operation. And we were just very graced and very lucky and blessed to have been able to play a tiny part. And they're big efforts that go way beyond us. So big kudos to them. Thank you for letting them, having them allow us to participate. So let's get to the meat of what we really want to talk about, right? Memory of Mars. So the outline of what I want to share with you today is basically moving, so sort of a story from the steps that I took as a graduate student from UC Davis, not too far removed from where you guys here are as undergraduates, and how that led me to kind of connect with NASA. And so I'm going to start with basically describing some of the cognitive neuroscience research that I did at Davis, that I was trained to do and had done thereafter, and how that kind of led to some steps that landed us at NASA on this mission studying cognition. And so again, then I'll sort of pivot from talking about brain waves and brain states that predict performance, and I'll pivot to talking about how we kind of looked at brain states and performance in this analog simulation. So in case I didn't mention what an analog was, it means that it's an environment like our HAB that is analogous to a spaceship. So analogous, analog. So they're called analogs. So does that sound like pretty good? Mm-hmm. If anybody was wondering, yes, that's my head. You see it?
I can see it.
Yeah, you can see it, right? So I actually scanned this actually during my postdoc time. I was a test subject for one of our experiments, and I was able to, I don't have the data from NASA because that's like highly confidential and protected, so I don't put that up here, but I can put my picture from my postdoc because I did this stuff. So all the stuff they're doing, I did. That's what I want to show, this connection between how neuroscience is informing NASA's mission to Mars. And so I want to start with the story about memory, and I want to introduce you to another core member of my team. This is my dearly beloved Juno. She is my greyhound puppy. She's a little bit bigger than a puppy these days, but I love her near and dear. And she really loves to play. She loves trail running. She loves to travel, loves the open road. And she used to like riding shotgun when she was a little puppy. She grew up a little bit more, and now she really prefers to drive. Okay? So this is a little bit about her, but I want you to think about memory now, because that's what we study, and that's what I'm going to be talking about. I want you to imagine if you only had memory for those sentences that I said, right? The black and white, just raw information. Juno likes to play, she likes to swim, she's lazy, she travels, she likes the open road, she likes shotgun, she prefers to drive. What if you had only memory for that semantic information, but you didn't have that rich tapestry of the pictures of the event? Would life be very rich and fulfilling? You'd be little robots running around, Snapchatting with no pictures, right? Yeah, it'd be awful, right? Yeah, okay, so that's kind of my contention. So I study episodic memory, which is our memory for all the the memory of the episode of everything that happened, the rich tapestry, the colors, the who, the what, the where, the when, all the stuff that matters, right? You want to remember not that your child was born. You want to remember the actual episode. I mean, days maybe not so much, you might want to forget that, but that's still a near and dear moment in your heart, right? I mean, that's your child, that's a special moment. You know, so that's what we focus on, and so the question that's sort of the central focus of our lab's research is sort of 3 points, which is basically, how do these episodic memories operate, and why do they fail sometimes? Secondly, how do we improve that memory performance for those episodic memories? And also see ways to maybe prevent the decline of those. Because I don't know about you, but my episodic memory fails all the freaking time. And we want to prevent that. And I'm not even that old. When I get old, it's going to go downhill real fast. Right? We want to prevent that. Now, the last thing we'll kind of ask then in relation to that is that, are there brain states that can be associated with this enhanced concept of cognition, if we can find ways to bump that up? So that's kind of what I'll share with you a little bit, some snapshots about some of the research findings that we've had, and there'll be overview summaries, and then we'll kind of move into the NASA thing. And so when I do that, kind of the connection between what I do and that'll connect with what we do with NASA is we'll see that we share multiple methodologies. That is, ways that scientists, both here at CSUSB or at UC Davis or at NASA, have available to take a snapshot of what's happening in the brain in order to understand our cognition and our psychology. So there's 3 main forms that we use. One is electrophysiology, which is basically you can record the electrical activity coming from the scalp using various different electrodes. You'll see it abbreviated as EEG. When we average, it'll be called event-related potentials, or ERPs. And you'll see it can look like this in some of the data I'll show, some graphs, or you can plot it in color maps based on the onset of a stimulus and the time of how that activity changes after the stimulus. Okie doke. Now the other thing we can do is take a look at it, plot it on where it happens on the head. So if you see this is a nose in the middle, looking down from a bird's eye view. You have a left ear and a right ear. So put the left ear in, you take the right ear out. The nose in, you shake it on the back. Okay, so that's EEG. The other thing that we'll do a little bit is look at neuropsychology. So we'll look at deficits that can happen due to brain damage. So we talked about this a little bit last time. We talked about being able to make some inferences on what brain areas might do or what might be happening based on deficits you observe after damage to certain areas. Now I can very thankfully say that I don't think we had any brain damage put to us in NASA, but you guys have to see how I teach the rest of the semester and give me a second opinion on that. Maybe you think they gave me some brain damage, but we didn't actually use that method. I'll talk about it in some data. And finally, we'll talk about some neuroimaging, which is fMRI, which is basically, instead of looking at really, really fast millisecond activity, that can look at the scalp location of brain stuff. Instead, we're going to put someone in an MRI machine, and what it's really good at is taking an inside view of a 3-dimensional snapshot of the brain. So this is a little bit slower time measurements, but you can look 3-dimensionally. Here you can look 2-dimensionally on the scalp, on the surface, but you can look much faster. And there are complementary methods that I use in research, that other researchers use, and that NASA is using as well. So I want to introduce you to that so you kind of know what we'll be talking about. Now, there's 2 big things to know about memory that sort of a good background primer that the field has kind of agreed upon. One is that memory seems to be based upon stimulus-response relationships. So anybody who knows about Pavlov's dogs, you remember our old friend Ivan Pavlov? He rang the little bell, and the dog began to drool. Okay? So you get the drooling dog. I need to replace that with Juno's picture, I think. She's cuter, but she drools less. But anyways, and we can see that that was a huge driving force in the field, led to operant conditioning, behaviorism, classical conditioning, huge part of psychology understanding of memory, right? Is that memory is a function of a response to a stimulus. Yeah? We'll talk about that, because I'm going to challenge that dogma. Then we'll also talk about the second thing, which is that long-term memory in the brain depends critically upon an area called the medial temporal lobes, and particularly an area called the hippocampus, which is kind of buried deep in there, in the middle part of the brain. Okay? Now, that sort of famous model has come about based on damage that we have observed, such that it's given us this canonical model that says there's 2 different kinds of memory, conscious and non-conscious, and the conscious memory relies upon the hippocampus, but if you have damage to the hippocampus, that your non-conscious memory is perfectly fine, because you can do that just right. So it's given us this division that non-conscious memory relies upon other areas, but not the hippocampus. And I'm going to try to shoot an arrow through both of these core pillars of the field. So I want to challenge conventional wisdom. All right? I'm going to see if you guys are persuaded by the time we're done. All right, so let's talk about that a little bit. The best textbooks all agree, right? Here's the thing, right? That non-conscious implicit memory, it does not depend upon the medial temporal lobes. This is told to us in the huge, thick Bible of the neuroscience field, like this thick. It's called The Principles of Neuroscience. It's written by this guy who won the Nobel Prize for Neuroscience and Memory that he worked on. And it says, it does not depend on the medial temporal lobes, our non-conscious memory. Okay? And it's not just him, it's also books by Gazzaniga, all these other really famous textbook writers and leaders of the field. Very common finding. But I want to suggest something, and it is the idea that what if we've been looking at a three-dimensional world with two-dimensional glasses? All right? What I mean by that is, what if we're looking at something in data, but we're only using maybe 2 methods, or maybe 3 methods might help? All right? And I'll elaborate upon that as we go a little further, because I'm going to ask, what if the hippocampus actually could be found to support our non-conscious memories as well? Okay? Maybe it doesn't, but why don't we look and find out? Okay, so it turns out that there actually is a hint of there being more to that story than what the textbooks had traditionally been alluding to. So, work actually by Wei-Chung Wang, who was in my lab at UC Davis, he's a good friend and an alumni from Davis. He found in 2010 that the medial temporal lobe can be sensitive to the status of items that we study, whether it's old or new, outside of our conscious awareness. It's really interesting. But it wasn't the hippocampus, it was a bigger area in the medial temporal lobe, so it wasn't quite the hippocampus. Now, we also found evidence from Debbie Hanula, who I was actually fortunate enough to learn from, because she was a postdoctoral scientist when I was just a little baby grad student at Davis. And she used eye tracking studies in patients with hippocampal lesions and found that the hippocampus did support signs of implicit memory, but it was generally associations. So it wasn't real clear, at least to me, whether it could be the associative role of the hippocampus, that's very well known, that was active for that finding, or whether it was single item memory. And that remained untested. So the suggestion that I want to make is that maybe these behavioral and MRI methods might not be sensitive enough to detect the subtlest forms of human cognition, which is the unconscious mind. And so, if you want to test with 3 measures, behavior, brain damage, and physiology, that would be a good way to do it. But the problem was that nobody had collected physiology of these implicit memory in patients who had had hippocampal selective damage. And the main reason for that was because, frankly, it's hard. It's really tough to do. It's hard to find patients. It's hard to get good data with low sample sizes. And we ended up only getting 3 patients who had selective hippocampal damage. But you'll see that they were pretty powerful data points. And so from that, I just wanted to, given the nature of our talk about space today, right? This wasn't collected because it's hard. But we landed on the moon because John F. Kennedy made a famous speech where he said, we choose to go to the moon, not because it is easy, but because it is hard. And so that was something that I was always drawn to, is doing things that are hard because they are hard. And anybody who will know me at Davis tomorrow knows that it was hard because we had a lot of setbacks. We had a lot of failures. And 5 years it took to test 3 people. All right? You hate your life a lot during those times. A couple points, okay? So it's tough, but we want to do it. And so I want to suggest, what if that hippocampus is playing a more fundamental role in non-conscious memory, maybe even a role that's necessary for it. So the question is, how do you capture non-conscious memories if you give these patients a conscious memory task? And I'll suggest to you that the answer is the same way that porcupines mate, which is very careful. Man, think about it. All right? Yeah. Okay, so creatively and carefully. What we'll do is we'll look for brain activity, and what you do is you compare the brain activity for when people say they don't remember, okay, this red line, okay? And you compare it to the time when they also say they don't remember, but this time they're right. It really is a new item. So their conscious experience is identical. That is, they don't have any conscious experience of that memory. But anywhere like this, where there's a difference between that biological signal, means that something in the brain is remembering, even though the mind has forgotten. And that's the strategy we'll use. This is data from what other people have shown in '98, showing this effect in this back area of the scalp. So I'm going to orient you to focus on the timing of this, which is about 400 milliseconds. And the physiology is important with that precision, but really we're going to look for this posterior area of activity that people have found in other experiments and look to see if it's there in patients without a hippocampus. And when we do that, what we see is a really profound pattern of effects. It's very surprising. In our healthy normal controls, we see that beautiful back posterior parietal activity just like we saw in that Nobel Prize winner's textbook. But when you look at people who don't have a hippocampus, this is that huge hole in there, you have a massive deficit. It actually goes south. And if you want to look at the actual brain waves for that, this looks a lot like our last slide. But here, our old items in black are going much further south. So it's really quite surprising. And it wasn't driven by one patient or two or an outlier. We can see here, this is the data point for all 3 of our patients. It's really quite substantial for controls and quantified by a reliable condition by group interaction or 2x2 ANOVA. So it's really pretty powerful findings suggesting that basically the hippocampus was impaired for implicit memory and that our non-conscious memory might be relying upon our same neural structures but functioning in different ways, such that a form of non-declarative memory seems to depend upon this hippocampus that it's not supposed to, because all the models say it doesn't. But maybe they're wrong. It seems that hippocampal damage seems to rewire the ways in which our old and new items are differentiated before awareness occurs. And so, maybe it blows up that model and might need some revision in the textbooks. So that was a pretty cool finding we had, and it led us to ask some other questions about things that might be happening in memory beyond our conscious awareness, particularly the brain states. So this is kind of like the part of the talk I started off with, talking about brain states for performance, and going all the way back to Descartes, which you guys are all experts on right now, because we talked about that last class, right? We got this idea that stimulus comes in and leads to a response. We have a stimulus of a bell, a response in Pavlovian conditioning, and even in neuroimaging, we've always modeled all of our neuroscience data of memory as a response of brain activity to a given stimulus. But studies of attention and sensation, particularly led by a lot of people at Davis as well, Steve Block, Ali Mazahiri, Jesse Bankson, they've done great work suggesting that neural state before the stimulus actually influences if and how somebody processes it. So we wanted to ask if that same principle of brain states can affect memory too. When we were at Davis, that's exactly what we did find. We found that this is stimulus onset, and there's a big pattern of theta frequency. There was much more bigger brain activity before stimulus happened that predicted. And by the way, it was located in this sort of frontal, left temporal parietal area of the brain. The bigger that this effect was, it predicted how good people's actual memory scores were later on once they were tested on memory. So it's pretty remarkable. We were surprised, very pleased. And so we did some follow-up studies asking what structures in the brain with MRI might be supporting that. So that's kind of what we did as a follow-up. We put them in that MRI, and we asked them to study pairs of information, either 2 words or 2 pictures, and we gave them this cue, pre-stimulus, and we wanted to know if brain activity here predicted how well they learned this information. So I'll show you sort of a summary of that. And it turns out it absolutely did. There are 2 kinds of activity patterns. One was deep in the brain in this hippocampus, and the other was way on the top, sort of right frontal cortex area, okay? Now, both of them actually negatively predicted memory, so that the bigger the effect was of brain activity, the worse you did. And I said, what the heck? This is really confusing. So we didn't know what to do, because we were correlating the size of this pre-stimulus effect with our measure of performance, which is the probability of a hit minus the probability of a false alarm, and they both came out in a multiple regression analysis as being independently accounting for separate variants. What that means is that these are different effects. This is not the same as this. This is not the same as this. And I threw my hands up and I went home and I said, what the heck do we make of that? And I thought about something. We said, we're correlating these 2 things to this metric of these 2 measurements. Why don't we separate these and take a look? And that's exactly what we did. So when you just look at the measurements of a memory hit, which is successful memory, it turns out the cortex doesn't care at all. But the hippocampus sure does. that's a big negative relationship. So the bigger the hippocampal effect, the worse likely you are to have a successful memory. But not for the cortex. But check this out. In the cortex, it really hugely cared about the size of the brain activity, because the bigger that brain activity was, the more likely you were to make a false memory, a false alarm, an FA. Which is totally not true in the hippocampus. Flatline. So this had never been done before as an analytic technique to understand brain behavior relationships in this regard by breaking down this metric that everyone's always collapsed together. Well, it turns out when you break it down, you can find out things are happening in really different ways at different parts of the brain. That was really cool. So that's kind of what we found there. Let's skip over this because I sort of summarized that, but the idea is we think that the cortex is more active during these false alarms because it's only remembering one item in the pair. So you're asked, hey, do you remember this pair? And you see one of them, and you're like, yeah, I remember that thing. And so you think you saw the pair, even though it's a different pair. And so it leads to a false memory. So you kind of lead someone halfway there, and they say, oh, yeah, sure, and they make the conclusion that's wrong. So it seems that our brain states prior to learning can predict both if and how the information is later remembered. And so, sort of summarize these brain states, we can see that both if and how a person will remember is kind of the interesting take-home point there. It can be both in the cortex and the hippocampus. So this is the first cortical pre-stem effects that had been seen. They can be both helpful and hurtful to memory. So it can make your memory better, or it can make your memory worse. And we think that the beneficial effects are reflecting basically better network optimization, better network communication among cells to support basically completion of the patterns that the neural networks are working with. And we think maybe the deleterious, or the negative effects, could reflect distraction that's happening in encoding, such that the more distracted you are, you're going to have more brain activity happening because you're distracted, and you're going to do less on memory, which seems to be a pretty viable account. We have some follow-up data. It turns out when we made some manipulations, we actually found that that was the case, but I'll save that for another talk. And the stuff that we're kind of following up with, actually Brooke Roberts just published this here with Charn at Davis just a few weeks ago, and they did manipulations because it gives us a target for interventions to improve performance. And that's exactly what they did. They manipulated brain activity using this cognitive entrainment method of this visual flicker. So you just put these goggles on, it gives you a certain entrainment frequency for the brain, and it turns out the people who got that scored better in memory than the people who didn't. That just came out a few weeks ago. I was lucky enough to be an author on it with them, but they did all the heavy lifting and all the hard work, and it was really an honor just to see the process that they did. So, so that's just came out. So it suggests that these stimulus-response models of a stimulus and response might actually be an incomplete account of the factors that are supporting our learning and memory. So, these targets for intervention for improving performance. Okay, so from this point, as a psychologist, right, I connected with some of the NASA side, and I realized that they were doing this big psychology experiment, and it turns out we need optimal brain states to support our cognitive performance, particularly in these really dangerous situations. Not in a laboratory here on campus. There's no danger there. This is real. Well, actually, this is a movie, but you know, you guys get the idea. So, so psychology, neuroscience, and teamwork are really key players here, and NASA understands that, and they're very interested in that. And so I sent an application in, and they called me back, and they said, hey, cool, you're a psychologist? And I said, yeah. And I sent my resume, and I said, this is all the stuff I do. They said, great, you will never do this mission. I got a call at like 7 in the morning. They said, hey, this is NASA. I was like, hey, how you doing? We just want to call you. We got the best resume we've ever seen. And we want to tell you permanently rejected. You will never do this. And I said, man. She said, yeah, well, you know, it's just that your background in psychology means you probably know too much about these studies in psychology. We need more naive research participants. So we just think that based on your background, you're going to know a little bit too much. And I said, ma'am, I think you have a misunderstanding here. I'm nearly half as smart as my resume seems. You can ask any of my friends. So, you know, we had a good time. She's like, well, we always need backups. We'll keep you on, like, the back burner. I'm like, hey, keep me in mind. You know, like, that's all I can ask for. Just give me a shot. And that's what we did. I didn't hear anything for months. Then they called back, and it turns out we got offered a position. First as a backup, and then I ended up moving in from a backup position to a prime crew. and this is our team. This specialized laboratory for testing these brain states needed for deep space travel. Our mission in particular was to go to this asteroid named Geographos. It's actually a real asteroid. Our job was to land. Our mission, should you choose to accept it, land, explore, and collect the asteroid samples, then return safely home. Right now, during this time, you are to live in 45 days of confinement. All right. So the upside to this is you have no internet, no Instagram, no Snapchat, no Facebook, no Twitter, no email, no text messages, no Bumble or Twinder or whatever, right? So the downside is obviously we're isolated from our loved ones, sunshine, and sleep. And you can see part of the joke I was shooting for here is that a lot of people that wouldn't be an upside. For me, that was kind of an upside. I'm not on Bumble or Twinder or whatever. So anyways, and obviously our job was to live as astronauts would live on Mars. And they told us that from day one. They're like, we are going to treat you like astronauts. We want you to act like them, which means act like yourself because you're selected for similar characteristics. But we are going to expect you to conduct this mission with that type of attitude. And we're going to treat you that way, and it's game on. And by the way, it's a sleep deprivation study, so you can't sleep much. But do a really good job. We're going to make you work here like dogs, like astronauts, from 7 a.m. till 2 a.m. at night. And no naps. Do your best, guys. You're on camera 24/7. Okay, bye. They didn't say bye, but then they said, get in the camera. Kind of. Actually, they trained us a lot. So that's what we did. Our job was to basically pretend living in one of these capsules that would be on a long-duration flight, and that is this capsule here. So this is our HERA capsule. Right, so we have some tiny living happening here. And I'll give you a little tour of the lab here. Whoa, hold on. Yeah. Make sure I can get this. Oh, yeah. So I'm going to talk you through a little tour. So we're leaving the airlock now. We're entering into the HAB. And the first thing we'll see, there's a big center elevator. Okay. There's a bathroom back here. Hot water, cold water in the shower. There's a 3D printer. It's our little engineering station. That's the exit. That's the big door in front. You got windows, pretend windows, stars, and they move just like you're moving. This is for operating the Canada arm, the robot arm I'll get into in a minute. You can see kind of a shot into our bathroom there. This is our flight simulator station where we do our lunar landers. This is our geology box. You work with simulated samples. Our medical station here. Our elevator that will rise up to the second level. And in a minute, we'll take a trip down the elevator from the second level. I'll come here in a second. Yeah, so now we're actually down. Okay, you can see we have a little exercise bike there. And we're starting to come down. You can see some of our storage units. Okay, those are all our food, MREs, if any of you guys were in the Army. Astronaut food. Here's our plants, hydroponic plant growth, and eat our vegetables. And here's our medical station, all of our supplies. That's the airlock where we do our virtual reality. Our engineering station again, our main door, the robot, the Canada arm, and again our bathroom. Here's our flight simulators again. We got a bunch of screens wrapping around. And there's our medical station. We do our scientific, like biology studies here. These are brine shrimp we're growing in comparing different salinities of 0.5 and 1.5. And this is our microscope, our glove box. Breath of fresh air. Then our flight simulator, we do lunar landers, and we'll also do our virtual reality explorations there. And of course, you can see a closer look at the bathroom here. You got our towels hanging. Notice no laundry. Got to wash our laundry in the sink. No dryer. Everyone's unmentionables hanging out, drying, hopefully not dripping on you too much. Yeah, you get to know each other well. See? There might be some clothes up there hanging. And this is our virtual reality setup where we would do our explorations in the asteroid. And we're just wrapping up here with our simulator again. And let's see. Oh yeah. Check this out. We got a 3D printer here. I'll turn the lights on for that in a second. And there it is. So we make everything. If you don't have it, something breaks, you gotta make it. Really cool. Got to learn 3D printing. And then kept track of our days. This looks like day 15. And of course, do not open this door until we're back on Earth. So, just in case anybody gets stir crazy and they want to run out. No, don't do it. So yeah, so that's kind of our crib. And you show up, day one, Johnson Space Center, super excited. 6 a.m. and this is what it looks like. This is Rocket Park. These are some of the rockets. And inside this big cap building here, this hangar, is where one of the biggest and most powerful rockets mankind has ever built. It's called the Saturn V. It landed us on the moon. And you walk in there day one and you pass that rocket, and man, are you reminded of how little you are in the world. And it is an incredibly awe-inspiring and humbling experience. This is what it looks like. And it was just incredible. Now, I have a pretty big head. Look at how big this is. Okay? So, anyways, really pretty remarkable. So you just show up to work just with all the awe and wonder and inspiration of a kid being asked to imagine being an astronaut on a spaceship. And they're paying you $10 an hour to do it. Like, what could be better? So we show up to work, human spaceflight hardware facility, authorized personnel only. This is our team walking in on the first day into our hangar. And my job at first was a backup to serve the team in the best way I could do it, and that's what we tried to do. This is a little journal I kept as a notebook, and this there is a scale, because we had to measure every piece of food that went into us and log it. And then their job was to measure every piece of food that came out of us and to log it. Yeah, science. So, so we got to do a lot of stuff. First we trained. They taught us everything we need to know. This is a lot of what I was very lucky to learn at UC Davis in the Neuroscience program. Kim McAllister, Elva Diaz, they just did wonderfully good jobs of patience, dragging me along to learn these things like mini PCR, DNA sequencing. We're culturing different bacteria here that Reinhold's doing, and then he's taking out DNA samples, and we're going to basically measure that DNA and sequence it, which is pretty cool. It's exactly what they use on the International Space Station. And this is us doing it in missions. It's called mini PCR, so it's just a tiny little way that they're sequencing DNA in these sort of biology experiments. We also did psychological experiments. So all of you guys, how many of you guys like surveys on Sona? Nobody. Guess what? I did this for hours and hours and hours and hours and hours and hours every single day. On our iPads here, filling out tons of psychological surveys, 10 cohesion questionnaires. How do you feel? How do you feel now? What about now? How do you feel now? Has it changed since now? Forever. I never want to touch an iPad the rest of my life. So this is sort of the second story of theirs. I was pretty happy. It looks like Shelley didn't like that test. But so we do that. We can watch some TV for nothing from the outside world, but you can bring DVDs. Paul was from, grew up in Minnesota, so he was a Twins fan. This is from the '91 Twins World Series or something. So we watched a lot of that. But my big excitement was, as a neuroscientist, we got to do a ton of neuroscience. And so you guys know about MRI. I got to do all three in one day. It was like a neuroscience triathlon. We got our MRI, our brain scans. We did something called functional infrared spectroscopy, which is a measure of blood flow in the frontal cortex that was linked to how we controlled the Canadarm robot. And then, what was really cool is I did an MRI for a mission preparing for Mars while I was wearing my Mars socks. So like, shows you how big of a dork I am. But like, that was pretty cool. I really like that. And then of course, as an EEG guy, this is what I was trained on for 15, 16 years. This is what I do. And to be able to do that at NASA with all these electrodes on was just truly amazing. And it was just shocking that after all these years of being trained, having no idea what would relate to space at all, how to do this research, right? And we all do this in classes and labs. I'm sitting there having NASA say the same things that my professors trained me to say and to do. And it was just a great reminder of how important that education was, how important and how good that training was from some of the best in the world that we were lucky to train with at Davis as well as College of New Jersey. So this is me way back in the Stone Ages when I was in college. I actually had hair. And this is me doing EEG back then. I was like 20 years old in 2001. And then now here doing it in NASA in a flight suit, lifting weights in the habitat. And I just couldn't be more grateful for the mentors and the training that we received at Davis from fantastic people. Steve Locke, obviously a luminary in the field, wrote the Bible of ERPs. Andy Linus, Jan Linus, Tron Ranganeth, and of course the colleagues Arne Ekstrom, Andrew Watros, and Javier Lopez Calderon. I drew so much from what I learned from these guys, and I loved I loved being the dumbest guy in the room with these guys, because it is really hard not to be the dumbest guy in the room because they're brilliant. So I'll get your question maybe afterwards if that's good. I want to work on time. So we also got to make friends. We had a Russian astronaut visit, a cosmonaut visit from the International Space Station, getting some big award at this ceremony. And it turns out we bumped into him at the hotel. I was able to practice the Russian I learned at Davis. And I said, "Говорите по-русски?" He said, "Да." I said, "Я изучаю русский язык, а ты куда?" He said, "Да." I said, "Немножко." And we made friends. We traded patches. Right? He gave us a sticker from his patch on the International Space Station with the Russian on it. It was just amazing. So we got to make great friends, build those international relationships up, and we've actually kept up kind of as pen pals, so to speak, trading letters in the time since, and he sends me autographs and stuff, and I send him things that he probably throws away. And, you know, I'm like, "Hey, we're doing this mission." He's like, "I'm an astronaut." You know, and I'm like, no, we're supposed to be faking it to be like you. He's like, "Yeah, I'm real." But he's an awesome dude. And then we made it through this rigorous training. We were ready to ingress into our capsule. This is the ceremony. They had a little bit of cake, some sparkling grape juice, and we were ready to go. They had a countdown to 0. Now, any of you guys here fans of 80s hair rock? Yeah, some 80s metal? All right, so am I. I'm a huge fan. Now, I was a wrestler in college. You know, I got to fight a little bit when I was at Davis with Uriah Faber and his UFC guys. So the big thing in that industry is you get to walk out to your match, right? They have you have your walkout song, sort of like in baseball. The guys walk up to the plate for the Dodgers or the Angels. You play their little jingle of the music. So I was like, all right, it's cool to get to do our walkout. And this is the only time in life, because if you're a real astronaut, they wouldn't do this. It's too serious. We got to go out on our final countdown to the 80s song of Final Countdown. And it looked like this. So this is kind of the transfer of command of the vessel from like a naval history, to our commander to now command the vessel. We have Wilson with us.
Team lead for campaign 4. Mission 2. I hereby officially put the vessel over. The commander and his crew all out. May his vessel provide you safe passage to Neuroscience and a safe return to Earth. Good luck with your mission. Godspeed.
I was really nervous about this point. I said, "Oh man, do I really want to go like in here?" This is about to get real. And if you look all the way in the back there, there's a small little face shot of one of the guys in the back was my little brother, who would never miss a chance to watch his big brother get locked up. So anyways, sorry, I don't know how that hit the wrong button there. Let's just okay. So here we go. We've seen the level 1 before. We've seen our tour through the HAB. This is kind of what it looks like as we walk in. This is where we slept, but only rarely. This was a sleep deprivation study. Really, just as an aside, really taught me how important sleep was. I don't care how macho you are. There's Army Rangers who have done this. We have, you saw our crew, a bunch of really serious, pretty accomplished go-getters. They asked us, "How you doing? You guys feeling good?" We're like, "Yep, grip it, rip it." You guys, you sure? And then they saw our scores and all of our tests were taken, and they were just at the floor. They were just getting crushed. So you might think you're doing just fine, but the data says otherwise. Sleep is so important. Please take care of yourselves, especially during the semester of classes and stuff like that. It really does make a difference, and it won't on the first day, but it will add up over time, and we won't notice it. And man, it's tough. So this is kind of the cool stuff we got to do, the virtual reality spacewalks. This is what my job was as a mission specialist. So I put on this virtual reality headset and microphone. get my flight suit ready, and go out and explore the virtual world as this fake astronaut. It was a lot of fun. Looked like this. We'd connect to this MMSEV, and it was a multi-mission space exploration vehicle, and we would kind of go off and explore the asteroid. We'd be controlled by these guys who'd be our teammates giving us radio commands, and if they ever had any questions, they got all the information they needed from Wilson up here. He's a very good compatriot. He was kind of our fifth team member, very, very beloved, near and dear to our hearts. He's a great listener, too. Gets a little cranky, though, in the morning. Anyways, so that's kind of what we're doing here. This is that simulator station we were on, and we'd go follow those dots, and they'd guide us with these laser beams. So that was really cool, and him and Shelly and I would work together to do maneuvers, and it was like flying aerobatic airplanes and diving at night and all together, and it was just really freaking awesome. And I was actually really aided in doing that by some of the training I got at Davis, because Davis offered scuba diving training and night diving training and research diving training. And I took it for a year and a half, and my professor didn't really know about it, but managed to squeeze it in, and without that training, I would never have been as nearly as comfortable to feed into this on short notice as a backup. So it was really good. Likewise with the aviation stuff, the radio command. So it was pretty good, and we had that good team communication. Here's Reinhold doing the flight simulator for landing on the moon. This is kind of what they're simulating, looking in there, and you're kind of following that trajectory on our digital maps. And a note here on simulations is that, this is important stuff, because, nobody just goes out and does it. But even Armstrong had a simulator. So this was his simulator for the moon. And a lot of the current generation, we don't know this, but he nearly died about a second later. He would have died. He had to eject. And history would have been changed forever. So he was simulating, and that's what allowed him to land on the moon, because they overshot their landing distance. He had to take the controls by manual and land about 20 seconds left of fuel left, or he'd be dead. So practice makes perfect, and failure does pave the way to success. So pretty inspiring. Other stuff we did, so we would grab these space delivery vehicles. So when SpaceX sends these supplies, this Dragon capsule, we've got to catch it on the space station, and this is the arm that we catch it with, our Canada arm. And we do this simulator for it, which is the exact simulator that the astronauts used to train on. They actually made ours tougher. And you've got to line up this crosshair on this pin, which is what grabs onto this and latches it together. And it's really tough. You have a lot of concentration, and they're measuring our brain activity while we're doing it. And that's kind of what it looks like here. We're getting that near-infrared spectroscopy measuring our frontal cortical blood flow. So that's kind of what we're doing. They're highly sensitive, and we get that good concentration and measure our errors. How are we screwing this up as we get less and less sleep? You missed that supply vessel? Guess who's not eating dinner? Where are you going to get the food from? Right? Really important. Can't afford an error of cognition. Psychology will make or break our trip. Got to have a handle on it. So that's what we're studying. And we did more of this EEG in the capsules. That was, again, really exciting. A lot, it just kept reminding me of all the training with Dr. Luck, Ranganith, and Yanalinas up there. Couldn't have been more grateful for everything they taught me, because we really got to really use it in good application here and helped us to succeed in our mission. This is me having some fun with it, wearing the EEG. This is our Joe, making a silly face for a little video we were making for kids at the time. And this is, they gave us a little t-shirt with EEG. This is an EEG cap. You guys probably might not recognize that yet. That's like an ear. This is a bunch of EEG. So I was being silly and goofing around. So that was pretty cool, because we started off doing that so early in our careers. And of course, that's what we do here at CSUSB. So we get to actually now continue that legacy. I'm going to show a ton of students here how we do that. I see a couple of you guys. I know we're getting started off in the lab, and this is, a lot of the students here from CSU that we're trying to do the same stuff. So maybe you guys be the next people on those missions, or taking those first steps as Martians onto that red planet surface based on some of the training that we're doing. So let's see here. We got a little bit of time here. I just want to kind of sort of transition into sort of the things that we are picking up during these stressors, right? We're getting all these measurements of our failing. We keep failing. We get all these tests. We're sleep deprived, and we're frustrated with people, and the team is getting stressed. And some of the things we learned was is that this is designed to stress your team. So one, when you're stressed, know that it's on purpose. There's nothing wrong with it. They're trying to do this. It's not a personal thing that your ego should be threatened by, that you failed on something, but that we're here as scientists to beta test this out. And so there's a good opportunity to kind of practice cognitive control and self-awareness, right? Not letting it get to you. Not letting the frustration beat you at that game. But instead, stay steady, stable, calm, confident, and focused, no matter what's going on. And so really that ability to be unshakable by these external events and stressors, that's a big deal. Something goes wrong in the spaceship, guess what? You got to still fly the spaceship. You can't let that stuff get to you. You got to still be unshakable even when there's a big blow up and everybody's all up in their business and the grill, and you got to stay cool. Really good practice for that. And one of the things I learned from it was this idea of service leadership, right? Always putting other first, because I was a backup, right? And I'm used to being in charge of this class. I'm used to being in charge of my airplane. I'm used to being in charge. But that wasn't always the case. I was a walk-on Division III backup wrestler in college, which translates in English to meaning I got the living hell kicked out of me day in and day out by a bunch of guys who were really good and I was really bad. So I had to remember how to be a backup, how to be a good follower, how to be a good supporter of a team by putting other people first. The way you do that is always put them first. So basically, the idea that I like to kind of have is that, I am nothing, we are nothing as individuals, but what's most important is the mission, what's next important is the team, and what's least important is me. By doing that, I was always thinking about other people. So I was always able to help them with something, which helped make the team move along. So that was something that was a really good learning lesson for me, and I think we can take that outside of the space capsule to whatever we're doing, in any of our group projects, by the way. You can see why I'm a big fan. But we also had a lot of fun outside of those stressors. If you can't see very clearly from the back, maybe you can guess which one of these is me. So, we had a good time. We had a really good team. Just great people that I was so fortunate enough. So all that stuff I just mentioned, I learned that from them. I was like the worst teammate on the crew. They were good. I learned how to be a good teammate from them. And, they say if you want to go fast, then you should go alone. But if you want to go far, you should go together. And, that is something that has absolutely resonated true. I never thought I'd give a talk about NASA, spaceships, neuroscience, and people would be sleeping through it. But history is made every day. And, that's okay. I thought this would be cool. But, yeah, people work. I get it. I'm just teasing. Anyways, so some lessons for living together that I learned, right? So one, just be good to people, right? One thing that we had a really good thing with our vibe on our team is like we would joke, we would have a good time. So you can see like kind of playful, like we would joke with each other on the team and stuff. That helped diffuse so many tough times. To have a joke, have a fun 80s song to play on the music that people enjoy or some other thing, but have a good joke. Get along with people, and that I can't really underscore that enough. The ability to take the attitude of being good to people and forgive them when they're not that way to you, because they won't be. Nobody's perfect. You're going to take some heat, but if you let your ego get hurt by it, then you're only letting it get worse. And so, things that I learned from better teammates than I was to talk less, listen more, think more, and really try to be at peace, because you can't escape this thing. You're locked in. There's nowhere to go. You can't fight with them. If you fight with them, that's not helpful. And honestly, in real life, it's not really that helpful either. Right? So those are really good lessons. Be patient, kind, tolerant, understanding. Work hard to really take their other point of view. Because you have to live together for another couple weeks and you can't get away. Right? You really got to, before you say anything, talk less. Think about what might they be thinking. And what I really want to say right now, how might that be interpreted by them? Could it hurt them? What if I'm just joking? But can I think about, I can see they're struggling today. Maybe they're not going to take it as a joke. Really, really helpful stuff that I found, right? Maintaining those positive attitudes, avoiding ego, snark, sarcasm, selfishness, all those negative attitudes can be toxic. And so it was a really good thing that I got to learn And really the core thing I took away was that if we can see all things, especially the difficult ones, as opportunities instead of obligations. So we had lots of stuff to do every single day that we hated doing and we didn't want to do. All day, every day. And sometimes we found ourselves, oh, we look at the schedule, oh, we got to do this today, oh, we got to do this other thing. But things really, really changed. When we said, oh, we get to do this. I get to do this task instead of I have to. Really fundamental shift from a positive mindset to a positive mindset, from maybe one that might have been a little bit more pessimistic. And that makes all the difference, not just for you, but it's contagious to the team. So that's something psychologically that really kind of picked up for me, because when you're living together well, it means you have to constantly look at how what we do can affect others, and maybe if we can do that all a little bit more on Earth, we might not ever want to leave it. You know? And so I'm not going to go through all this right now because it's probably short on what the time is that I'm trying to hit. But you know, some things, like I said, is that, you know, do you have to do something or do you get to? And you know, find the best in the situation, the reasons to smile, the ways to laugh, opportunities to serve the other members of the team, because you're tired, you're hurting, you're not in a good mood sometimes. None of us are. And when you're locked up, that stuff gets exacerbated. And we don't want those catastrophic failures on the mission. We don't want it at home, in our families, at work, you know, in our school groups, and we take that for granted sometimes. So that really kind of was a very helpful way to learn a little bit about here, because really the take home from this is complaints don't make spaceships fly faster. You know, they make them go slower, and it's already a really long trip. So those things really made a difference. And so, you know, moving forward, you know, the thing I would suggest to you guys from the mission is that we can't really reach Mars without a better understanding of the neuroscience, cognition, and psychology. It's really important stuff. NASA understands that. There's funding opportunities for that. We need other scientists like you guys on board to help get involved, design good studies, get involved, work together with this. And there's funding opportunities that NASA has through the NSPIRES grant system, through the Human Research Program. They're leading the way forward. And, you know, good scientists, great scientists make for the best teams. And we need to add more to that because these errors in cognition and selection, we got to figure out who do we pick, by the way. How do you pick who goes? Humanity's never had to make that decision before. How do you pick who's going to get along? Buzz Aldrin, Neil Armstrong, they're only together for about 7 days, 9 days. You can kind of tolerate anyone in that time period. This is very different. We've never had to make this decision. But figuring out how to make the right selections will determine if we have catastrophic effects. And so, you know, to bring that back home, the science here is obviously essential, but at the end of the day, like we were just talking about a minute ago, I really want to suggest that it's our humanity that we're going to have to rely upon, because more than anything else in these missions, you've got to be good to people. And I think we can take that outside of the mission too. You know, when Frank Borman came back from being the first person to circle the moon in the 60s, he had this quote where he said, when you're finally up there at the moon looking back on Earth, all those differences and nationalistic traits are pretty well going to blend. And you're going to get a concept that maybe this is really one world, and why the hell can't we learn to live together like decent people? You know, and that's something we don't get to think about a lot, because we're in that little spot. It looks different than that spot, which is different than that. But when this is your view, and that was awesome about this mission, no Twitter, no Facebook, no news, no anything. None of that mattered. We didn't care. It was awesome. And we got to just think, you know, of ourselves as they asked, as astronauts. Not as citizens of a country, but as you know, members of a species. And I think that was really changed my view coming out of a bigger thing to think about. Because again, we may never want to leave Earth if we can do that a little bit better on Earth. So with that, I just kind of want to leave you guys with this message to kind of, you know, dream, believe, and do, right? You know, you got to have dreams. You know, I was dreaming to do stuff like this for years as a little kid. I never really thought it would connect. But you know, they're not really able to be done without believing in yourself. And being in this space with that huge rocket ship I showed you, I was there by myself one day, and it made me realize how many smarter people there were than me that for whatever reason weren't there. And I I wasn't very smart, I wasn't very fast, I wasn't very good at anything. I wasn't the best at much anything, but I realized that the reason that I had been there and been lucky at the time is because I believed in what my dreams were. And other people gave up. That was really kind of the difference. So I really want to sort of communicate that, because that's real. It's not cliche. It's like you sit there and you're like, wow, I'm really dumb and I can't believe I'm here. There's better people than me and I know who they are. But somehow I'm here because they gave up and I didn't. And that was really profound. It makes you feel very small in the world. But it happens, and that's the way it does. And you know, you can't just stop at believing. You got to actually do it. And it really can come true, and it can happen. You know, I say that just to share that experience, because it's not a cliche. And you know, there's Journey fans in here. Don't stop. So with that, you know, I want to thank the HERA team, the HERA crewmates. I learned so much about being a good teammate from them. They helped me to become better. The broader team at Mission Control were fantastic. Certainly want to thank the audience here, everybody at Davis, all the memory researchers that I got a chance to work with. Elva Diaz was chair of the admissions committee, and I have no idea why she admitted me, but I'm so grateful that she did. So I'm always indebted to that. Of course, the HERA team and Mission Control, the mentors I've had along the way, and the people here at CSUSB, basically the people who run my lab when I'm off adventuring doing these things. Lindsay Sirianni, Alana Muller, Rose DeCock, who's now a student at UC Davis. She went there, just graduated from CSU last year, got a $300,000 worth of free scholarship to go get paid to get a PhD. So these things can happen. Like I said, it's not cliche. These things, we make it happen. We make these things happen. And of course, the psychology department and the dean here has been incredibly supportive. So I want to thank that, the diversity program in neuroscience who helped support that training here at Davis. And I really want to sort of say nationally thank you to everyone who helped during Hurricane Harvey. I didn't have a chance to talk about it during this particular talk, but our mission was aborted, with an emergency abort in the middle because we took a direct hit from Hurricane Harvey last year. In Houston, our Mission Control members' houses and cars were underwater. We were surrounded by hurricanes, tornadoes, and everything else, and told to get all of our stuff out of the hab in 15 minutes or less, and we got to get out of town. And so I saw the real devastation and the people that suffered. I can tell you firsthand that for those of you guys who contributed and helped our fellow citizens down there, people, it really made a difference. And it's easy to forget about now, but that was a big thing I wanted to sort of just thank the people outside of Houston for. So as we make this journey to Mars, remember that, you know, hopefully we can make it, but I will try to persuade you that we can't make it without the brain there. So keep that in mind, and I guess that's probably all. I'll stop at that. But yeah, that's kind of our mission. That's kind of the idea of the talk. That's that. I know I had a question over there.
Yeah, so...
Can I have 1 second? I welcome your question. If you guys have questions, I can maybe answer one or two fast. I have to jump on the airplane very soon to go lead this talk. So I do want to talk about it. Let's do it. I want to let you guys know that I'm not trying to be rude, though, if I duck out in a couple minutes. But please email me questions, ideas, comments if you think, hey, dude, this one or two slides, stop talking about it. Didn't matter. Or you're way too fast, you're way too slow, or this was boring, this is cool. Please hit me up. I'm very much welcome. So anyways, what's your question?
So they didn't turn off gravity in that particular thing.
We don't know how to do that yet.
So they're hoping to sort of have a compartment in which gravity is there for the trip, or no?
I don't actually know, to be honest. Yeah, be cool either way. Yeah. Any other short questions? All right, awesome. Well, thank you guys for your patience. Thank you guys very much. It really is an honor to represent CSUSB there, and to try to bring some coyotes out that direction. And we have more missions coming up in the future. Hopefully we'll get some more coyotes involved in some student activities for it. So thank you guys very much. It's very, very fortunate to be able to share it with you guys. Thank you. Okay.